going to prove a nice limit theorem. It goes as follows. Suppose the following. If f and g are two functions with the following properties, such that the limit as x goes to c of g of x is L, and the limit as y goes to L of our f of y is equal to f of L, then the limit as x goes to c of f of g of x is just f of L. Now let's just look at that a little bit more closely. What is f of L? Well, it's f of L. But L is this. It's the limit as x goes to c of g of x. Now, what is this really saying? How can you go from here to here? Well, the limit can go in there. You can pull out the f. You can pull out the f. You can put the f in front. That is, take the limit of this, there it is, and then take f of that. That's what it's saying. Well, let us prove this. And like always, we prove things using definitions. The limit as x goes to c of g of x equals L. Okay, so the first thing we want to do in the proof is to state what this really means. What does it mean that the limit as y goes to L of f of y is f of L? Now, since we know this limit exists, given any epsilon, there does exist a delta. We don't have to find it. So this statement is the same as, given epsilon greater than 0, it does exist a delta 1 such that, I'll write it a little bit differently than I normally do. The difference between the y and the L is less than delta 1, guarantees us, it implies that f of y minus f of L in absolute value is less than epsilon. Now, I'm going to call this statement 1, and on the right side, statement 2. But we're going to rewrite these a lot. This statement means that y is in between L minus delta 1 and L plus delta 1. For y cannot equal L. So on a number line, here's L, here's L plus delta 1, here is L minus delta 1. And y can be anything but L. That's y. But that implies, well, what does this mean? This means that f of y is in between f of L minus epsilon and f of L plus epsilon. Okay. So here's my L. Here's my f of L minus epsilon. And here is my f of L plus epsilon. And f of y can live in between here. This is where f of y can be. Now, I want to update the graph this graph right here. Suppose y equals L, okay? Suppose y equals L. Well, if y equals L, does that imply that f of L, because y is L, I'm copying this, minus f of L in absolute value, which by the way is 0, is that less than epsilon? Of course it is. So if y equals L, everything's okay. That is, we can fill that in. We're going to need this. So statement 1 implies statement number 2. If you have this, then you're guaranteed to have that. Okay, now let us draw a line here and let us look at the second piece that we have. We have this piece here. Let's see what that means. The limit as x goes to c of g of x is equal to L. Well, what does this mean? That's the same as, and we know this limit exists, it's given epsilon greater than 0, there is a delta. There exists delta such that the difference between those two is less than delta, but positive. Whenever that's true, we'll call this statement 3. Whenever that's true, then the difference between g of x and L in absolute value is less than epsilon. Now, I'm just going to move that over a little bit, give myself half the board to do half the work. G of x minus L is less than epsilon. Alright, so what does this mean? This means that this means that x is in between. X is in between c minus delta and c plus delta. But x cannot be c. Okay, can't be c. Can't be everything, you know? So here c minus delta, c plus delta, x can live in here. That's x. Okay, and that's also statement number 3. Okay, this implies, well, what does that mean? That means that g of x is in between L minus epsilon and L plus epsilon. So here's L plus epsilon, L minus epsilon. G of x can live in here. And this is statement number 4. That is statement number 4. Now, if I choose epsilon to be delta 1, that means this will be L minus delta 1. And this will be L plus delta 1. And L would be in the middle. Okay. So, statement 3 implies statement 4. Now, if I let y equal g of x, that's another thing that's important. Y is g of x. So, this is y. Now, I claim that this is exactly the same as statement number 1. I claim, as I said, I'm going to let epsilon be delta 1. So, this is basically saying that y is in between L plus delta 1 and L minus delta 1. Now, that's exactly something that we have before. let's see. Y is in between L minus epsilon, sorry, delta 1, and L plus delta 1, including L, just like statement number 4 has. It allows L. So statement 4 and statement 2 are the same. What statement? These are the same statement. Now, statement 2, statement number, oh, sorry, this was statement number 1. Statement 4 and statement 1, they're the same, and 1 implies 2. Statement 1 implies, there it is, implies statement 2. Statement 1 implies statement 2. Okay, so let's put this all together. Statement 3 says that x minus c is less than delta but positive. X minus c in absolute value is less than delta but positive. That implies statement number 2. Well, what is statement number 2? It says this. That is, more importantly, it says this. F of y minus f of L. F of y minus f of L in absolute value is less than epsilon. And this delta exists. So, given any epsilon, the delta exists. By definition, this statement means that the limit as x goes to c of this equals that where y is g of x. The limit as x goes to c of f of g of x is f of x. And let's just confirm it. Let's go all the way to the top, and this is what I wanted to show. F of g of x, the limit equals f of L. The limit of f of g of x equals f of L. Long proof, but we got it. We actually composed it, which was a